With this problem, we have basically looks like it might be a fork or something like that that is actuated with a hydraulic cylinder. And let's see what we know here. We know that the pressure that is generated in the hydraulic cylinder there is 110 psi, and the problem actually gives us a little hint in there. It says that the amount of force carried in a hydraulic cylinder like this is equal to the amount of pressure times the area of the piston head. Okay, and so we know for this problem the diameter of that piston, and that from there we can get the area of the piston head. So that's kind of a little twist that goes along with this problem. We also need to do sort of the statics part of the problem, which involves doing what, you think? Okay, we probably will at some point need to sum some moments. Before we sum moments, what's the step we should do before that? A free body diagram, right? The summing moments is doing an equilibrium equation. That equilibrium equation arises from the free body diagram that we draw for this system. So what we need to do then is determine what body should we draw a diagram of. And that's a lot of times the first tricky part, is figuring out what we want to do the diagram of. So what do you think? Give me some ideas. Okay, the fork body. I like that. So I think the suggestion is basically this body that goes from A to B and then underneath this crate of alligator meat. So I like that. One thing that I'll show you here is if you have time, I actually always prefer to draw the free body diagram so that it looks accurate, so that the body itself looks like the actual body. But if you are trying to do a problem quickly, the most important thing you do for your free body diagram is make sure all of the points that you care about are correctly represented relative to other ones, and just draw as simple as possible of something that connects all of those dots and show that as your body. So what I'm pointing out with this is that you don't necessarily need to draw an accurate fork exactly like it's shown over here. What do you think is important to draw? Like maybe, show how A connects to B, right? So you have A and B, then what else? Maybe where this fork comes over like this. Okay? You don't have to spend a ton of time drawing the body, is what I'm basically saying. It's okay, it suffices as long as you take all of your points of interest and represent them, in a at least roughly accurate way relative to one another, then that's good. Okay? Notice here I did not include a picture of the cylinder. All right? I'm excluding that body because what I'm trying to get is the force carried in that hydraulic cylinder or hydraulic ram. All right? So I'm excluding that because I want to represent that as a force that will ultimately be on this picture. Okay? So now what? I've got the body drawn. What's the next step to doing my free body diagram? Okay, you can put dimensions on. I'm okay with that. Where is it important to include some dimensions? Okay, some of them we can probably just copy over from what we have on the original picture, right? So like right here. Okay, we know how high it is relative to this point right here. That's 3 feet. So we copy that over. What else you think? Okay, maybe relative to this right here, how far is it horizontally over to this location? So that looks like it's 5 feet on there. Okay, the alligator meat, it's the center of that is about 2 feet over from this spot, right? So I could show, before I can really draw that, let me actually draw that force, right? That's one of the reasons why we often start by drawing vectors that represent forces. Sometimes we do that step first, but I'll go ahead and draw that on here. We don't know the weight of the alligator meat, right? So let's go ahead and put that on there as a variable. Okay, maybe just WT or something like that. That's a variable. And how far is it from point A over to where the alligator meet weight? Okay, that's 7 feet over to there, right? Okay, so far so good. What else do I need to do? Have I gotten all of my forces acting on this fork body? Have I represented all of the forces that act on that body yet?
No.
Okay, what am I missing?
Just on that C to B.
Okay, so from C to B, there's the force in that ram or hydraulic cylinder thing, okay? And that is something we have enough information to figure out how much force is actually carried in that body. One thing I'll say about it is this body connects from one point to the other. So it connects from this point right here to this point right here. It is connected only at 2 locations, and it's connected with frictionless pins. So if we have those conditions met, it's connected at only 2 locations, and at those 2 locations it's connected with frictionless pins, and I guess a third condition that no other forces are acting on it either. No outside forces come in and act on it, which means that we'd have to do things like neglect self-weight and that kind of thing. But if we do those, neglect self-weight, and go ahead and deal with it that way, what we can say about this body is that the force acting in body CB is going to act along a line that extends from C to B. Okay? We know the direction of the force that acts in that body is what I'm saying. Okay? The next thing I want to do is actually look at that body CB. Let me actually draw sort of a little simplified version of it. Let's say this is the, body CB. There's a couple of different ways that this body could experience this force, right? One way it could experience force is that it would try to make it shorter. If the forces acting on the hydraulic ram try to make it shorter, it would be like this, right? Those would be the forces acting on the ram. This is a compressive force that I've shown right here. What's the other possibility? Okay, the other possibility is there could be forces that tend to try to make it longer. And what's that? Yeah, that, or tensile is the word that we usually use for that, is tensile forces, something that tends to try to take something and make it longer. What would you like to assume as far as the force in our body there? What do you think the type of force is that acts on that body? You think it's tensile? So you feel like the forces acting due to the weight of the alligator meat and the fork and everything, you feel like that would tend to try to take the cylinder and make it longer. Okay, it's the other way, right? It would tend to try to take that cylinder and make it shorter. So that's like the red arrows I've got up there. It's going to try to take that thing and push it in and make it shorter. Okay? Well, if that's the direction of force that acts in the hydraulic ram, then what direction does that mean force acts on the fork? Body AB. What direction does the force act at point B? Okay, because remember, this is point C, this is point B. Point B is also up here. And what I would say is Newton's third law says that that force would act equal in magnitude, opposite direction to the one that I showed right here. All right, because that's the same force actually. It's just you're seeing that force from the standpoint of the cylinder or the ram versus the standpoint of the fork. Okay, so let me go ahead and name that something like maybe F ram. Okay, and that's that force right there. Okay, any other forces that act on this body? Like, are there any at A, for instance? Okay, what happens at A? It's a pin, which means what? Okay, yeah, it's not allowed to move left and right. It's not allowed to move up and down. So there must be forces in those two directions that prevent it from moving in those ways, right? So I'll call that R-A-Y, and this I'll call R-A-X for reactions at A in the X and the Y. Okay? All right, so now what? Is there any other information I could put on my diagram here that would be helpful? I feel like there are two pieces of information that would be very helpful to have on my free body diagram. Let's see if you can come up with what they might be. Okay, I wrote FRAM up there, okay, but I can figure out what that value actually is, right? How do I do that? Right, FRAM, I can do that according to what this says up here, right? It says the force carried in a hydraulic ram can be measured by measuring the hydraulic pressure in the ram and multiplying by the area of the piston head. Okay, so what does that give me here? 110 psi. That's the amount of pressure. And what do I need to multiply by? Okay, I know the diameter here is 1.5 inches. So given diameter, can I find area? Okay, I should be able to. It should be what? Okay, pi r squared, or the other way is if I have diameter, the other way you can express that is with pi d squared over 4. Okay, and if you look at this, what is PSI? Do you know what PSI means? Okay, it's pounds per square inch. What do the units do if that's pounds per square inch? Okay, yeah, you'll notice there that the inches squared that I have right there would cancel the inches squared that I would have right there. And what do I end up with? Pounds, okay? So I'm in good shape as far as that's concerned. So let me go ahead and punch this in here. 110 times pi times 1.5 squared divided by 4. Okay, and this gives me how much force I actually carry in that ram. 194.39, we'll say. 194.39. pounds. Okay, and that's this FRAM that I have right here. Do I know anything else about that force? Okay, I know what direction it goes, right? It says that that angle is 70 degrees relative to vertical, right? So if that's 70 degrees relative to vertical there, I can show that. This is one way I could show it. That's valid. Okay. And I think that basically gives me most everything. Only thing I'm lacking now is sort of a technicality, but it is always a good idea to put your coordinate system that you're working with on the diagram. Okay? But I've got all the information that I need to be able to deal with this problem. What's next? What do you do with a free body diagram? What's the next step after you draw a free body diagram? Yeah, so equilibrium equation. Someone mentioned that right at the beginning. Equilibrium equation is what you do after you've drawn a free body diagram. The equilibrium equation that's most useful to us is anything that eliminates the things that we don't care about out of the expression, but retains, the best is if we retain one variable that we care about and eliminate everything else that we don't care about. So what expression, what equilibrium equation does that for this problem? I think some of you may have already mentioned it. If you sum moments about point A for this body, okay, and I'll take counterclockwise to be positive, what you see happens there is RAX and RAY, which are unknown forces. Since they have lines of action that pass through A, those two forces will not appear in this equation. Okay? Only ones that will are the weight that I have, which is what I'm trying to find, and the 194.39 pound force that acts at B. Okay? So let me write this expression now. I've got, let me start with the weight. Okay? What direction does the weight try to rotate the body around point A? Clockwise. Is that the same or opposite what I said was positive? Opposite. So that means I use a negative weight, which is one of the things, that's what I'm trying to find, times what? 7 feet. Okay, then what? Okay, I need to look at the 194.39 pound force. It actually has a directionality to it of 70 degrees relative to vertical, and the location of point B relative to point A is also not simple, right? It's got two components for that length value that goes from A to B, right there, right? And so, how do I deal with that? Okay, probably the most, I would say, formulaic way of dealing with that is to split the force into components, one of which it goes horizontal, one of which goes vertical, and then deal with each of them separately. Okay, so what I mean, graphically speaking, is this. I'm going to take this force and have a component of it that's here and a component of it that's here, and look at the amount of moment that's created by each of those components individually. Which one do you want to start with? Okay, the y component first. Okay, I'm good with that. Okay. What direction does that y component tend to rotate the body around A? Counterclockwise, which is positive according to how I've defined it in this expression. Okay. So there I've got 194.39 pounds, but I don't want that entire force. I just want the vertical component. How do I get just the vertical component? Okay. I do want the cosine function. Why cosine? Yeah, it's the adjacent component, okay? So that much of the expression there, 194.39 pounds times cosine 70 degrees, gives me my vertical component. Then what do I do? Multiply it by, okay? I need the distance from that line of action of the vertical component to point A, right? I need that distance. Which is what? 5 feet, right? And that takes care of the vertical component. What about the horizontal component? First of all, does it tend to rotate it clockwise or counterclockwise? Counterclockwise, which again is the positive direction according to how I've defined my sum. Then what? Okay, I need to take 194.39 pounds and multiply by the sine of 70 degrees. That picks off just the horizontal component because it is opposite of where the angle is measured, right? And that much gives me my horizontal component. What do I need to do to make it a moment? Multiply by, okay, its line of action was right here, and so it is 3 feet from that line of action to point A. Do I have any other forces that would create tendencies to rotate around point A? assuming we neglect things like self-weight, let's say. I think that's it, right? So we can set this equal to 0, and we can solve, right? Let me pull up my calculator here. Does everyone know how to store a variable in your nice Casio calculator? So I hit Shift, and then above the RCL key, there's this STO. If you hit those two and then hit one of these buttons where you have A, B, C, D, E, F, it allows you to store that value into a variable. That can be useful sometimes. I'm going to use that technique here. So what do I mean here? So how am I going to use that, you think? And I'll tell you what. I'm going to go ahead and enter this expression all, like it is, only for weight, I'm going to call that capital X. Okay? So I'll say negative X times 7 plus, instead of typing 194.39, I'm going to hit, what do you think? A times the cosine of 70 degrees times 5 feet plus what? A. Okay, and to get A, I don't know that I touched on that very specifically, you hit this alpha key, and that actually gives you the ability to put in that variable A, times the sine of 70 degrees times 3. Okay, and once you put all that in there, you hit alpha, and above the calc key, you'll see an equal sign. You're going to set all that equal to 0. And with this calculator, you can just hit Shift, and above the calc key, you'll see solve. Okay? The first thing it does is it says, is this still the value you want to use for A? You say, yep, that's what I want to do, so you hit equals. The next thing it does is it says, would you like me to solve for X? And I say, yep, that's what I want you to do is solve for X. The number it shows you at this screen is what it currently has stored in X, and that's what it's going to use as its initial guess when it does its iterative technique inside of it to find the solution. You don't necessarily care about that, but that's why it gives you this screen right here. When you hit equals, it will now solve for what that variable must have been. 125.77 is what that ends up being. And that would be in units of pounds. Okay? So what's the answer? Okay, or up here in the choices that are given, you would select 126 pounds. Okay.